In the first part of this video, we saw that dark matter would behave like a black hole, capable of retaining time inside. If there had not been an inversion in the direction of the arrow of time accompanying the Big Bang, the observer could not have been endowed with a memory that would allow him to talk about his past. The theoretical stretching of space by dark matter before the singularity event would result from negative work. The resulting force would point in the opposite direction to the formation of space curvature. In this movement, there would be an increase in elastic potential energy. To illustrate, the same would happen when you stretch a spring. The light, which in the future will be projected into the interior of space-time, should accompany the appearance of the curvature of space, becoming polarized and deviating towards the red. This characteristic of light, being polarized within dark matter, is used by science in the Doppler effect nowadays. However, the accommodation of light to the increase in the curvature of space could not be accompanied by acceleration, as this increase would result in the contraction of time. Without the measurement of time, there could be no measurable movement. Even so, if there were real motion that we couldn't measure directly, it would have to be delayed. That is, potential energy would predominate over kinetic energy. The latter is who would support the movement. Therefore, the concentration of matter at a single point in space would result in the total collapse of motion. Acceleration would be integrated into light only after reversing the arrow of time. For science, this would have occurred at the exact moment of the Big Bang. Before it, time and space did not exist, for all intents and purposes. Therefore, it is possible to notice that the stretching of space and the acceleration would belong to different phases of the harmonic movement of light. We are only now citing light because the messages originating from dark matter, which also describe the curvature of space, would have been encoded in electromagnetic radiation and not in space itself. Thus, as in practice, it is thanks to light that we see the expansion delayed, or as the result of a late projection of information into our past. If space were to participate directly in the communication process, we would not need time to become aware of distant events. Another expected consequence of the contraction of time during the formation of the curvature of space by dark matter would be the leveling of the energetic extremes of light. That is, even if the ultraviolet and infrared have been pushed away from each other during the formation of the curvature of space, heading towards different poles, the contraction of time would equal these two extremes. At least, until the exact moment when the arrow of time reversed itself in the Big Bang and light was projected into space-time. In this inversion movement, the observer would be placed in the center of what he could observe. Thanks to the mentioned leveling between the infrared and the ultraviolet, the light, which would have been projected in the past of the celestial dome, would assume the appearance of circular waves, which would be superimposed over time. This arrangement of waves, like building a house of cards, would result in the formation of the future light cone of events, defended by physicists. The separation between celestial bodies would become possible only in the contraction phase of space, even if they had all been clustered in the same two-dimensional plane until there was an inversion of the arrow of time. The main consequence of this leveling between the energetic extremes of the radiation would be the circular motion. It seems to prevail in our dimension, observable by light. Both the image of the sun and the other stars appear to move across the sky with constant velocity and acceleration. Thus, one might think that, if the ultraviolet and infrared started from the Big Bang with the same speed, and from the same moment in time, there could not be a real polarization of light in space-time. The most logical conclusion would be to predict a depolarization of cosmic radiation after the inversion of the arrow of time. The Doppler effect would be a kind of optical illusion, as it would use polarized light at a time when it should already be depolarizing as a result of time inversion. That is, the hidden depolarization of light would allow us to see its own delayed polarization. Science also postulates that all matter in the universe would have been concentrated in a single point in space, smaller than the eye of a needle. Along with this matter would be the light. Thus, even if, after the inversion of the arrow of time, light seems to move in space at a constant speed, following the distance between galaxies, before the Big Bang it would have been, simultaneously, everywhere in space. Or, as science predicts, over the same extremely dense spot, smaller than the eye of a needle. According to this model, instantaneous and long-distance communication would finally become possible in post-Big Bang space-time. Newton would be happy if this prediction came true. Nor could it be proved that light would move in space absolutely, since it would be, at the same time, at the origin and at the destination. From the point of view of light, there would be no departures or arrivals. Instantaneous communication is predicted to exist at the subatomic level of matter through entanglement. However, when it comes to observation, there is no difference between the levels of matter, as they all depend on the same form of remote tracking of light. A classic example of instantaneous and long-distance communication is the fact that, if the sun were to go out now, it would continue to shine in the sky for another 8 minutes. After that time, the darkness would instantly manifest itself to us. Before that final moment, we couldn't even suspect that something wrong could be happening to our star. Astronomers tell us that space-time would show us only a small part of dark matter in its illuminated form, around 10%. These 10%, which make up the observable universe, would carry, with them, some characteristics typical of dark matter, which would appear to the observer in a time-phased manner. For example, the late projection of information on the celestial vault tells us of a constant increase in the curvature of space. It looks like our event horizon would get further and further away from us. Even so, a hypothetical increase in the curvature of space should be accompanied by a gradual deceleration due to being indexed to the predominance of potential energy. The light seems to be describing, with a delay, an event that would have happened within dark matter or in our future. However, Doppler tells us that, in space-time, expansion would appear accompanied by acceleration. For those watching the expansion from the center, time appears to delay or slow down towards his event horizon, following the redshift. In the dark matter universe, however, the virtual increase in the curvature of space would contract time unrecordably. If time did not dilate after the inversion of its arrow, an event that would have happened in the moment after the Big Bang, the observer would not be able to count on a memory. Intelligent life could not have arisen in the observable universe. As time dilation could not be predicted to happen with dark matter due to its very high density, it is deduced that, in the visible universe, the curvature of space could not be increasing in real time. The acceleration would be real to us, but not the increase in the curvature of space. as the acceleration would result from a constant decrease in the elastic potential energy within space-time. Space should already be gradually losing its curvature and tending to become flat. At the present time, all matter in the visible universe should be gradually and continuously losing density. A trend that would have been suspended to infinity, at least when it comes to our point of view. We could illustrate this hypothetical event by dropping an extremely dense star into space. As it aged, it would lose density and increase in volume. Even if its mass did not change significantly, the curvature of space around the star would become increasingly shallow, with space tending towards its original 2 dimensions. It can be seen, in this case, that the curvature of space would be gradually undone, following the loss of the star's density. Another example, to be cited, would be Saturn. Its density, per cubic meter, is less than that of water. Thus, if the planet were placed in a pool, it would float. Placed under the same conditions, the Earth would go straight to the bottom of the pool. Although space appears to be increasing its curvature during expansion, the opposite effect is what should be expected. Galaxies are moving away from each other faster and faster because space would be contracting in real time or losing curvature. In this case, the acceleration would not be due to expansionary movement, as the line tells us. As light has a fixed and limited speed, there is no doubt about the assertion that the informative Big Bang and the continuous expansion would be seen with a delay or outside its own time.